Modular Tech Talks is an exclusive series featuring internal presentations from our engineering team, explaining the inner workings of the modular technology stack. In this edition, Caverly gives a tour of the Max Pipelines architecture, covering its major interfaces and how they enable the modular team to rapidly bring up state-of-the-art models with high-performance features like KV cache optimization and speculative decoding.
This is our third in the series of Modular Tech Stack bottom to top talks. Today, Kyle's going to talk to us about pipelines.
What I'm going to be talking through today is Andrew tackled last week, talked about the graph. I'm going to essentially pick up from where he left off, starting essentially at the max graph and working our way up to serving. This is primarily going to focus on two individual pieces, those being the max pipeline, and I'm going to briefly talk about the scheduler, which is like a weird pseudo object that lives between the server and the pipeline. So to start us off, what I'm going to do is I'm going to kind of break down, there's three primary pieces to the Max pipelines. I'm going to start by talking about two kind of fundamental packages, those being the Max NN module and the Max KV cache module. They serve as kind of like the backbone, the lowest level of the pipelines implementation. I'm then going to kind of step one level up, walk through how we actually implement our models in our pipelines architectures module, and then wrap it up with actually discussing the pipelines themselves. I'm going to be walking through the vanilla text generation pipeline. I'm going to talk about the constraint decoding pipeline and the spec decoding pipeline. To start us off, I'm going to touch briefly on the KV cache. There's a bunch of objects that we use inside the KV cache, but essentially its intention is the lowest level primitives that we use to manage and manipulate the cache. So we use things like a cache strategy, which is like if you've heard of like page versus continuous batching versus the naive cache. And then there are two primary objects, those being the manager and the collection. The manager is essentially a high-level object that manages the cache and the state of the cache, and then the collection is the actual object that we pass through the graph, which contains individual tensors that we then pass through our attention kernels and whatnot. And so the KV cache module at a very high level breaks down two things: core, which are these primary abstractions, and then specific variants. So we have a collection and a manager for page cache. We do it for continuous batching and the naive cache, etc. Really straightforward, super complicated, but for the purposes of this talk, I'm not going to dive too much into it. The next one I'm going to talk about is the Max NN package. So Max NN is pretty analogous to like a lot of NN modules you'll see in Torch, etc. And what it is essentially commonly shared model layers and ops. So it is the first layer between the Python Max Graph API and our models. And the intention here is that it serves as the bedrock for any model implementation downstream. So as we implement a new model and we can abstract a specific layer away, we expect to move it up to the Max NN module. This module does not really depend on any configuration or implementation details surrounding orchestration or managing the pipelines themselves. It's really focused on three things. So a core abstraction, the Max NN module, which I'll talk to in detail, and then two things: primary ops and implementations. And ops can be a variety of things. Primarily, we have a package called the NN kernels. These operate as our custom op wrappers. So for every time that we have a custom kernel for something like the fuse, QKV mapmul, and attention, we're actually going to create a wrapper that operates here. It's essentially meant to be staged inside a graph at a later point. We do something similar for something like clamp, which is not a primitive exposed to the graph API, but a super simple op that we can stage in Max NN and use downstream in a lot of our other implementations. The hope is that our samplers also live here as well. And then the last thing, the core or most important piece of Max NN is a lot of these implementations. So we'll include our primary abstractions for stuff like the transformer block, and the attention with rope in this package. And what this allows us to do is make improvements to our fundamental architecture pieces without having to rewrite these for everything. So for example, the vast majority of our models If you think of Mistral, Replit, Llama, a lot of the original models will all share this same transformer object. And the expectation is that this is essentially functionally declared on initialization. And abstracted in a way that we don't have too many model-specific details handled at max_nn. We expose new functionality and expect model implementations downstream to pick it up. Pretty straightforward. The one piece that I'm going to speak to in more depth is this concept of a max_nn module. This is some new work. There's a design doc. I know Kathy has spent a lot of time moving a lot of our layers over to this. It's done a lot of things for model building. Specifically, it's standardized and organized a lot of how we build our models, specifically around device handling, weight handling, etc. It improved the ability for us to actually build our graphs, specifically surrounding weights. So we used to have a requirement in which we had to have weights before we could actually build the graph altogether. With the max_nn module, we're now able to essentially remove this requirement until model init time, which allows us to build a graph with randomized weights and then load checkpoint weights in at a later time. This is like super effective for stuff like smoke testing or just essentially quickly evaluating if an operation will build. It's also necessary for things downstream, like way downstream of us, like training and etc. if we wanted to get into it. As I said, it standardizes the interface for working with devices and individual weights. And then it also allows us to build in kind of additional layer hooks for debugging. And this is super useful. We used to build a lot of our layers in this super ad hoc way. And this has standardized the way that we build a lot of these layers and compose these subgraph elements up into larger graphs. And this is going to be super important even moving forward when we start talking about like expanding our metagraphs at the pipeline level for compilation time and a few different things. And this kind of sums it up broadly. What we used to have is we used to have this concept of a pipeline model, which I'll talk about. And we would actually communicate directly between the pipeline model and the graph. This is a super broad interface. And what it ended up causing was just a whole bunch of ad hoc work in the middle. We didn't really have like a primary layer to interact. Now, after NN module, the expectation is that the pipeline models will call to NN modules, which then manage the interface directly with the graph as well. This just cleans up a lot of the boilerplate that we had when creating individual layers. I'm going to talk a little bit next about how we actually implement a new model. So given that I've discussed these two primary building blocks, the max_nn and the KV cache, I'm going to talk about, well, how do we go from these kind of fundamental building blocks to something like the Llama architecture? And there are three primary pieces to building a new model. The first is we actually have to implement a primary interface, which is the pipeline model interface. This lives in the Max Pipelines module for a specific architecture. The second piece is we actually need to identify which tokenizer is used for this. And this tokenizer, importantly, is on a modality specific basis. So we're going to have one pipeline model for each individual architecture, but we really only need a tokenizer for, we have two tokenizers, and I'll kind of talk to them. One's for text and one's for text and vision. And most of the time you do not have to implement a new tokenizer. I have one question here in the chat. So the question is, how do we actually work the mental model between PTs and then module and R module? It's quite similar in some ways. I think like loading weights into the object or moving it between devices, etc. There's not been a lot of content created that kind of like maps this out effectively. I think that sort of content would be super useful. I know one of the large goals of the max_nn module project is to make graph building in Max more analogous to something like Torch, right? So a lot of our layers now operate much closer to how we used to do it in Torch. how we do it in Torch versus how we used to do it in Max. A good example is like our new MLP layer that Kathy put together, or even like comparing that to the way that we used to build sequential layers. It's like night and day as to like how familiar the interface feels versus that. But I do think that'd be great content for us to put out. Perfect. So then, as I was mentioning, we're going to have a series of tokenizers. And then the last piece that we need to do to implement a new model is actually register this with the pipeline registry. I've talked about this registry quite a bit. Essentially, what the registry does is it makes sure that we have a single point of config for a particular architecture, and that's accessible downstream by any user, whether that's in a like API process like Max Serve, or whether it's used in kind of the LLM interface that we have for offline batch inference, or I believe Max Builds is even using it for validation as well. And I'm going to walk through each individual piece. So the first thing is we primarily implement the pipeline model interface. So this is an interface that's responsible for essentially constructing and compiling the Max graph, preparing model inputs, and executing the model. What's important to keep in mind for this is that the pipeline model is a compiled Max graph. So that's kind of at the point at which we bridge between graph execution and Python inputs. And while the tokenizer does manage for specific input preparation like tokenization, etc., the pipeline model manipulates specific inputs like tokens or image inputs into model-specific inputs, the actual tensors that they're expecting on the devices they're expecting to run on. And it actually manages for execution as well. Most notably, though, these are logic producers only. So these do not include sampling or anything like that. The expectation here is that we have essentially a series of inputs, which roughly is a token sequence. And we're producing this variable hidden state tensor at the end. And it is not the responsibility of the pipeline model to manage what happens after that tensor is created. It is the reason that we can actually use the pipeline model interface for both text generation and embeddings, because the expectation is output is not a token, it is this embedding vector. And what we'll have is we'll have an implementation for each individual architecture. So you'll often hear us talk about these architectures relative to their Hugging Face config architecture. So we're going to have an implementation called the Llama 3 model, for example, that implements the pipeline model, and that is aligned with the Hugging Face architecture Llama 3 for causal LM. The new Llama 4 model is aligned to the Llama 4 for conditional generation. And essentially, what this interface allows us to do is it allows us to load a Hugging Face config that aligns to any of those architectures, and load a kind of parameterized version of that graph that fits with the config provided. This is how we're able to like hot swap and support all these different models. We may have one architecture for Llama 3, but we're able to pass it any Hugging Face compatible config that is specifically aligned with this architecture tag. Right? I think this has been super beneficial for us. We used to handle things in a wildly different way. So that's the first kind of piece of implementing a new model. The second is identifying an appropriate tokenizer. So as I briefly touched on before, each model expects to have a tokenizer associated with it. This is our pipeline tokenizer interface. And it really has one specific job, and that is converting the token generator request to the input context. And this includes two things, primarily tokenization and modality-specific preprocessing. So the tokenizer will include both tokenization and managing things like downloading images, etc., or working with encoded images in base64, etc. It also manages decoding, of course, when we're actually returning this back to the user. And we have to have a different variant of the tokenizer for each modality. This is kind of similar if you're familiar with like the Hugging Face concept of a tokenizer versus a preprocessor. Our tokenizer concept encompasses both both the tokenization and the pre-processing necessary. And we'll have two, the text tokenizer, which is used by basically everybody, and then the text and vision tokenizer, which is used for Llama Vision and Pixtral. Cool. And then, so once we have a pipeline model built and a pipeline tokenizer identified, the responsibility is then that we actually create a config file. These are called supported architectures. This is a Python class, which answers kind of four primary questions. Um, to Brennan's question, he says, if every model is a transformer, then pre-processing and tokenization are synonymous. That's true, but we also have to manage for different things like image manipulation and stuff like that. And that I don't think is tokenization necessarily. Okay, so the supported architecture will answer four questions, those being the pipeline tokenizer. So like which tokenizer do we actually want to use for this model? The pipeline model, which model do we actually use? We separate out the pipeline task at this stage as well. Is this for text or is this for embeddings generation? This helps us downstream actually select the pipeline we want to run. Do we want to run the text gen pipeline? Do we want to run the embeddings pipeline, etc.? And then it also allows us to provide a series of cache strategies. So what you'll notice is like often now we're pretty good with the maturation of the page cache, but when we were developing the KV cache, what you would see is like a lot of models would support one cache strategy, but not the other. A good example is like Mistral doesn't support the naive cache, for example. So we need all of this information in order to generate the pipeline, which I'll talk to before. And so for each architecture, we will have this individual kind of config file set up. I have the example here set up for Llama. We'll have something like the text tokenizer, the Llama 3 model. I'll say this is for text generation, and we have a page cache strategy as the default. And then our pipeline registry has a process which will essentially collect all of these configuration files and allow us to map this particular pipeline configuration versus this like a Hugging Face architecture ID, such that when you invoke the CLI, we can actually retrieve all of the associated pieces of a pipeline, those being the text tokenizer and the model, to actually construct and run the pipeline. Kind of looks something like this. When we initialize on the CLI, we'll send from a pipeline config through to the retrieve function. This does a bunch of validation, identifying if we support the architecture. It'll identify if it's vanilla text gen, spec decoding, if constrained decoding is enabled, etc. And it'll return two primary objects, the pipeline tokenizer and the token generator. And I've highlighted the token generator because this is the primary piece of the pipeline implementation that is model agnostic. So once we've moved beyond kind of implementing an architecture into actually generating tokens. And so this object, the token generator interface, actually includes the pipeline model itself. And these are the two primary objects that are used from both serving or benchmarking or any of our internal use cases. They both have specific APIs on them that are required to run token gen in full. And yeah, just to reiterate here, the three primary interfaces that we've kind of talked to is the pipeline model. This is used to construct, compile, and execute an architecture-specific graph. The tokenizer, essentially given a request, prepare modality-specific inputs that are relative to both the modality and the pipeline model itself. And then the last piece that I'll kind of focus on for the rest of this talk is the token generator. And it has one goal, and that is to generate N tokens as fast as possible. So yeah, the token generator interface is essentially responsible for three things. It's responsible for fetching the KV cache collection. So what this does, every time we have a series of inputs, we actually have to go to the KV cache on the machine, generate a Mojo object that we use to actually hold information related to the cache, which we then pass throughout our kernels. It is also responsible for executing the model graph. I have S in brackets there because a single pipeline can include more than one model. That's a very important distinction we introduced with the kind of arrival of the spec decoding pipeline. The token generator is also responsible for sampling, and it's also responsible for multi-step scheduling and orchestration. And orchestration is a broad term here. but it includes things like generating inputs for constrained decoding. It also manages moving data to and from device, etc. And that's a really core assumption with this token generator, is that it plays probably one of the most primary roles that we have currently right now into performance related to data transfer. So the way the interface is outlined is we are expecting an input into the token generator from the CPU. And it is the token generator itself that actually manages data transfer from the CPU to the GPU and back. As the expected return from the token generator is again this text generation response object, which is on CPU. This is super important because you'll often hear us talk about what is the Python overhead in the next token loop. And I can talk about why it exists and what we were looking to fix it, but it all comes down to essentially this interface. We're expecting CPU inputs in the door, and we're managing all of this transfer in this kind of pipeline metagraph. Yeah. It's also important to note that the pipeline is like in this semi-state of statelessness. So objects like the token generator, the pipeline model, and the pipeline tokenizer are, for the most part, stateless. These are essentially graphs that take a series of inputs and execute against them. But there are two primary pieces of state, those being the input context object, which contains essentially in-flight sequence information, and then the KV cache manager, which manages what portion of the cache is allocated, how do we get more data from the cache, how do we write into the cache, etc. So with that, I'm going to walk through kind of 3 examples of our pipelines right now. Well, I will talk about the pipelines individually. We do have 2 pipelines. Some of this work is included in the same code. If I take a step at looking at the text gen pipeline, which is our kind of vanilla generation pipeline, we primarily take 3 things: the page KV cache manager, like a cache manager, a pipeline model, and a sampler, and use those as our primary inputs. These are again configured by the pipeline registry. And what's really important to understand here is that they are compiled subgraphs. So we do not have a single graph which will interact with the cache manager, the Llama model, and the sampler. We will actually have different graphs, and we're expected to pass tensor values or tensors into these different graphs throughout the pipeline. I think we're looking to change this in the future. What we have is we end up with these processes where there's a weird mixture of Python-related code and graph-related code. But as the API for the graph API becomes more expansive, we've found that we can take more and more into a single graph. We'd like to do that for 2 reasons. One is simplicity. It's harder for us to work with a code that'll essentially compile a Llama model and then compile a sampler and pass between them, versus just composing these 2 objects correctly, constructing one metagraph at the top level, and executing against it. This is going to be impactful, especially as we move beyond vanilla text generation setup to something like pipeline parallelism, or we're talking about the async single-step scheduling work. It's also super impactful for spec decoding, because a lot of the time when we have to step out of the graph, we're going to ultimately lose performance in some regard. Most notably when we have to go between CPU and GPU, but that's going to be a primary focus, is actually cutting this down in the future. But if you take a look at the pipeline, we will have, it's pretty straightforward. We'll have a context object that comes in the door. This includes a series of in-flight sequence objects for the entire batch. We will then take this and go to a single compiled graph that returns to us KV cache specific inputs that are then used for inside our kernels throughout the pipeline model. We will then actually execute the pipeline model subgraph, pass those through to a sampler, which is again an executed subgraph. And then we will augment these inputs in flight without returning from the GPU. So we'll actually augment these inputs on device and then do what we call multi-step scheduling in this instance, where we will essentially go back up and rerun it through the pipeline model for an indeterminate number of steps. So if you're asking for 5 tokens, we can essentially execute these graphs very quickly, 5 in a row, without moving back from the GPU to the CPU, generating additional tokens and removing the data transfer. And then at the end of those multi-step the multi-steps, we just return the token array as generated. This also manages for stuff like EOS tracking and maximum length tracking, etc. All of those additional work are done on the CPU and affect performance because we cannot essentially, we should be able to schedule that work in some instances on the CPU and allow for greater utilization on the GPU without all of this work happening on both devices inside the single operation. And so we may be exploring ways in order to do that moving forward. One of the other features that our pipeline actually includes is what's called constrained decoding. So at a high level, constrained decoding is primarily focused around the idea that we can generate this finite state machine, which can accurately predict the next possible states for tokens, and provide essentially a masked tensor that we can use to say, hey, this token is valid or not valid, etc. And we can use this to constrain the output space of generation and generate valid JSON outputs in the most traditional case. And all of this work is maintained in the pipeline as well. So with constrained decoding, we've introduced this new external object. We use XGrammar. We have this concept of a grammar matcher, which is actually responsible for the finite state machine management and the bitmask generation. And what we'll do is we'll start by updating this FSM, so identifying what are the next available states. What we'll also do is something called jump ahead decoding, which is where we can essentially collapse the future states of the FSM into a single pathway if possible. So for example, if you think of a JSON, the first object of a JSON is always the left curly bracket. And so the jump ahead decoding piece will actually say, hey, there's only one available token. We don't actually need to go to the model at all for this. And we'll fill our context object. Again, maintain state in the FSM before moving on. And so once we've kind of reached the end of the collapsible single paths for the finite state machine, we will branch into the prior pipeline in a similar fashion. So we will take our inputs, we will go and run a compiled graph to actually fetch and retrieve these KV cache inputs. And we will pass both the input context, the KV cache inputs, through to the pipeline model to execute. We will then sample this and return the tokens. Most notably, the one big piece that you'll notice between this and the other one is that we cannot run multi-step scheduling with our constrained decoding pipeline. And the primary reason surrounds the creation and the update process on the finite state machine. So this lives on the CPU. And essentially, if we were to try and enable multi-step scheduling, we would have to return the data from the sampler to the CPU, update our finite state machine, generate the new bit mask on CPU before passing to the GPU to continue the multi-step loop. And from a performance perspective, I don't think we should expect any increase in performance if we're continually going to and from the CPU and device in this context. So we've kept it simple, in which there's no way that you can run both constrained decoding and multi-step scheduling until we can actually manage for generating the bit mask on GPU, which is not on the horizon. All right. And the last pipeline I'm going to talk about is a spec decoding pipeline. This looks a bit Frankenstein. But essentially, What we've done is we've actually doubled the amount of subgraphs that we include in our spec decoding pipeline. So for each model, essentially at a high level, spec decoding will include two models, a draft model and a target model. And the expectation is that you can run 5 tokens in an autoregressive fashion through the draft model before evaluating these 5 tokens at a target model, and then essentially doing something called rejection sampling to identify which of the 5 are valid tokens. And so in order to construct this pipeline, what we'll do is we'll actually create two versions of each model. So we'll have a Llama 3 model for a draft model, say an 8B model. We'll also have a Llama 3 model for a 70B model. And then we'll actually have an associated KV cache manager that is associated with each particular model. So we'll have one for the draft and one for the target. And the way this pipeline works is it'll essentially pass through the draft model in the exact same way that we pass tokens through in the vanilla text generation pipeline setting, in which the multi-step scheduling number of steps is equivalent to the number of draft tokens that we're looking to generate. So we'll generate 5 tokens through our draft model, use these to essentially augment the inputs on device. And once we've generated these draft tokens, what we can do is we can actually, again, go to our KV cache manager for the target model, retrieve the appropriate KV cache collection for the target model, execute through the target model, and then rejection sample, which is a separate sampler that is used specifically for this purpose, in which it'll essentially take in both your draft logits, your target logits, and reject, accept, and sample new tokens from the target distribution before returning the object. This pipeline, this pipeline is very challenging to work with in our current API, mostly because of this assumption that the pipeline model is expecting inputs on the CPU and managing for moving them to the GPU on their own device. Right now, the primary perf improvement that we're looking for on the spec decoding pipeline actually surrounds making sure that we do not have to go round tripping from the GPU to the CPU back to the GPU between the draft and the target model. And this is, again, an artifact of the fact that when the graph API was in its infancy, it was much easier for us to manage state in Python than it is to manage all of this in the graph. Now that we've expanded this a lot for performance and a few different reasons, we'd love to get to the point in which each of these objects, namely the cache manager, the pipeline model, and the sampler, are all treated as subgraphs. And the pipeline is essentially responsible for orchestrating these subgraphs and creating a single max graph that we can then compile and execute against. This makes it way easier for scheduling. It also helps us a lot with regards to like moving data to and from devices, etc. And that's going to be a really interesting kind of future area that the team has to tackle. So before I move on, that is like a speed run of everything up until the text gen pipeline. Go ahead, Josh.
I wanted to ask a question specifically, though. It seems like there's a lot of really kind of well-factored layers here, probably from, the experience, we'll say, of like not having good factoring. Like you said, maybe at the beginning, things were just like directly to max graphs. I'm kind of curious if you or the team have thought about like exposing this to external users, right? Like as libraries or something. Is it on the radar? Like I feel like there's a lot of conceptual complexity that we've compressed here into these layers that people could really maybe use outside. I don't know. What's the thought about that?
Yeah, I think I know the team's talked about like when we open source pipelines as a whole. I think for the most part, the current code base is at a point at which I believe you should be able to essentially, if you had access to the code base, namely the interfaces on the pipeline side, you should be able to actually use the max NN module for the most part to construct a new graph and register with the registry and work with it even outside our direct code base. we have spent a lot of time. I mean, it's definitely not perfect. There's a lot of work that we still need to do in cleaning up some of these interfaces, but we've seen a massive improvement. And I guess, yes, Brennan mentioned it's already open source. We've seen a massive improvement with regards to our own iteration speed, right? I know we still are working on tons of ways to get better, but a lot of the work for Llama 4, for example, on being able to stand this up in 2 days relies on us having like really great abstractions lower down the stack, right? And the challenge with that is that a lot of the time for us, the pressure is on implementing a new model, right? And it's much harder for us to actually take those and abstract them appropriately and move them back up the stack. And that's something we can definitely do better at. We don't do it for all of our model pieces. For example, like what's common, and I think the modeling team can confirm or correct me, but a lot of the time we'll first implement our kind of functionality in the pipelines in the specific architecture before moving up to NN. And it's that moving up to NN that we often miss. And I think if we're going to expose these as a public interface and encourage people to use these libraries, we'd want to essentially make sure that we're pushing as much up that can be abstracted well, such that it's easier and easier to build new models in the future for users.
Cool, thank you.
So next week, I think Deep is going to be discussing max serve. But what I thought we should comment on is essentially how does the server interact with pipelines. I'm going to talk a little bit about the scheduler, what role that plays as well. And then, yeah, we'll go from there. So assuming we have two objects, these tokenizers and the pipeline, how does serving actually interact with these? So I'm sure Deep is going to be talking about this in more depth next week, but we essentially run two primary processes. And I'm not going to get all these details right surrounding the API worker and the model worker, but this is how Pipelines thinks about it. I can give you that. So there's two objects that the pipelines produce, those being the pipeline tokenizer and the token generator. And essentially, at a very high, simple level, serving is going to have two processes, an API worker and the model worker. The API worker is going to be responsible for taking requests in the door and passing them through our tokenizer. And this is going to create this kind of like modality-specific context object that is stored on the API worker. We then, once we have this input context object, we'll cross like the process boundary and send this to the scheduler. And the scheduler is essentially responsible for coordinating and passing inputs to the token generator that are most optimal. And that lives in a separate process in a model worker. This distinction is actually one of the trickiest parts of implementing anything in the pipelines architecture because there are often inputs that we have and we want to maintain on a context-specific basis that we can't cross the boundary with for like, we've run into this whole bunch of times with like pickle issues and things like this. But it's one of the most like kind of important pieces of this because it does limit our ability to do certain work in certain places. Like for example, if the API worker has a lot more room to run, we could have additional benefits in a constrained decoding scenario by actually compiling the grammar matcher, maintaining it on our API worker, and creating our initial bit mask and jumping ahead on the API worker before it gets to the model worker. But because of the way that XGrammar is managed, we actually can't cross the process boundary with this. So it actually does constrain the architecture that we have downstream on the model worker at the token generator stage specifically. And the scheduler kind of in a different way does allow for us to have more capacity here. And the one thing I'll say, I'm not an expert on the scheduler by any means. But what we've found is that recently there's a lot of areas in which the scheduler is starting to interact with the pipeline quite a bit. And I do believe that moving forward, more co-design between the scheduler and the pipeline is going to like bear fruit for us over the long term. We even found this like last week, for example, in finding that we were doing redundant work between the scheduler and the token generator, especially when it comes to us focusing more time on removing the overhead in our token generator loop, being able to actually manage the two processes in a way that we can do certain work on the CPU and allow us to keep the token generator GPU or device only may yield additional performance improvements in the future. Great. So the last thing, and I'll kind of just briefly touch on the scheduler a bit more. But at a high level, it's really responsible for one thing, and that is creating optimal batches for token gen. It uses like an async queue process to essentially manage both context encoding and token gen batches and then passing them to our token generator. What we found is that as the pipeline is getting more complex, namely surrounding ideas like constrained decoding or speculative decoding, there ends up being like weird edge case bugs in certain scenarios in which the scheduler has to like implicitly identify whether we're in a token gen batch or a context encoding batch. And those concepts of like context encoding versus token gen structurally mean less and less as the pipelines get weirder, right? So this is like a very clear concept if you think of like a vanilla text gen pipeline with multi-step scheduling, but it is much less a clean concept when it comes to like implementing constrained decoding at the token gen stage or implementing spec decoding within the token generator. So I think moving forward, yeah, again, I think more co-design between the scheduler and the token generator will be beneficial for us. It's kind of odd that both the scheduler manages scheduling and the token generator manages scheduling. And I think over time, as we kind of continue to push for perf, and a few new projects come up, notably something like disaggregate prefill or like async single step scheduling work being done, we're going to see this interface be cleaned up a lot more. In my ideal future, I would imagine that the token generator ends up being basically a single graph execution object, and either the scheduler or the API worker does more work in actually preparing inputs on the CPU, moving them to the correct device, and executing them before we get to the token gen stage. This is going to be increasingly important as we get into like a multi-node scenario and stuff like that. Right now, all of the logic surrounding what device you're running on or anything like that, or what device needs what data to run the pipeline is managed at the pipeline level. And that's going to limit us based on how it's built, with this expectation that we're only receiving CPU inputs and only returning CPU inputs. And that is the end of the pipeline speed run. Thank you.
Awesome. Thank you, Kyle. That was really great. I certainly learned a ton.